Hello po, kami po ang Group 4 na magre-report ng heating load computations for building. 4.1 Heat loss in buildings. Heat loss is the amount of heat that a building or building space loses from heat transfer during cold weather. Heat loss. Yung heat loss, ito yung total measure ng heat transfer mula sa loob palabas ng building. Nakadepende ito sa size, sa type, at sa weather condition and sa climate ng lugar kung saan nakatayo yung building. The heating load is the heat that the HVAC equipment must generate and introduce into the building to maintain comfortable condition in the building interior. Heating load, ito naman yung amount ng heat na kailangan ma-produce para ma-maintain yung comfortable condition ng temperature sa loob ng building. Transmission heat losses are the result of heat passing through a material in the building envelope or through assembly materials. The quantity of heat transfer may be calculated through each material and for each mode. Transmission. Sa transmission naman, ito yung paglabas ng heat through the building materials, for example, sa glass, sa wall, sa ceiling, or sa floors. Infiltration heat loss relate to air leakage through the building envelope and the energy required to heat unconditioned air that has leaked into the structure. The air passes around or through the building envelope. In every building, no matter how well constructed, there is a certain amount of cold air that leaks into the building, referred to as infiltration heat loss, and an equal amount of hot air that leaks out. So yung infiltration daw, ito daw yung pag-leak ng air through the building. Madalas to nag-occur sa doors and windows. Ventilation is the introduction of outdoor air into the building or parts of the building at a controlled rate with the intent to maintain or improve indoor air quality. Ventilation heat losses are tied to the energy required to condition outside air that is intentionally introduced into the building. Yung ventilation naman, ito yung introduction ng outdoor air papasok sa building para maging fresh yung hangin sa loob and namamoderate nito yung temperature sa loob. Madalas yung air na ginagamit sa ventilation is hinihit muna bago i-introduce sa building. Units of heat loss. Sa heating, ventilating, and air conditioning industry, metric or SI units and US customary units, madalas inch, pound, or IP units yung ginagamit. Sa heating sector naman, yung quantity of heat loss or uppercase Q is madalas ine-express siya sa units of measure of BTU or WHR. Yung rate of heat loss naman or lowercase q is ine-express siya in BTU per hour or W. Ginagamit din yung Roman-based numerical prefixes sa IV units, C for 100, M for 1000, and MM for 1 million. Yung BTU per hour is ini-express din as BT per H, BTUH, or uppercase BTUH, or sa mas malaking units, MBH or MMBH.
So, I'm Ryan Christian M. Rodriguez and I'm going to report transmission of heat loss. Transmission of heat loss in construction. Transmission in heat loss computation. Transmission heat loss is heat loss through the building envelope. Heat loss through a building assembly is calculated by multiplying the coefficient of heat transmission, U factor, by the area of assembly and difference between inside and outside ambient temperature and the time period. In equation form, transmission heat loss Q or rate of transmission heat small q are found by, yan po yung formula, where U is the overall heat transmission coefficient in BTU per hour Fahrenheit, Ft2 or W over M2 Celsius. A is the area in feet to M2. Delta T is the temperature difference in Fahrenheit or Celsius. T is the time period in hours. Q is the quantity of heat loss in BTU or W minus R. And Q is the rate of heat transfer in BTU per hour or W. The area A of the construction assembly, example, wall, ceiling, floor, that is between the heated and unheated spaces. Note that delta T is found by subtracting the outside air temperature from the air temperature of the heated space. Delta T, outside and inside. Typically, these are design temperatures. The various portion of the building envelope may differ in the amount of heat conducted through them, and they differ. U factors are values. Such differences will depend upon the conductive qualities of the materials used in each section. The concrete used in the foundation, wood in the wall, glass of window, and shingles of the roof all have different conductive characteristics. Heat transfer analysis is required for each of the different construction assemblies of the building. So, example, a house has 1,000 feet squared of net exterior wall area. After subtracting the window, doors, and so on, the outside air temperature is 0 Fahrenheit and the inside temperature is 68 Fahrenheit. So A, compute the rate of heat loss through the insulated wall. So ngayon, yung formula kanina nandun naman sa last slide. So ito lang 'yan. U times A times delta T. So 0.073 BTU per hour times Fahrenheit feet. So just 100,000 feet squared. So ito yung sagot. Magiging 4964 BTU per hour. Compute the rate of heat loss through the installed wall. So yung U natin is yung 0.267 BTU per hour. So gamit yung formula kanina, ang makukuha ang sagot is 18,156 BTU per hour. Sa C naman, compute the transmission heat loss through an insulated CU. U is equals to 0.073 BTU per hour Fahrenheit feet squared over a period of 1 day 24 hours. Oh, so gamit kanina yung formula, ang makukuha natin na sagot is 119,136 BTU. So, let's tayo sa susunod. Transmission heat loss in construction assemblies below grade. Earth is an excellent conductor of heat. 1 foot of dry earth has R value equals to about 1. However, Earth has the ability to absorb huge quantities of heat over a long period of time, and then release the stored heat over an equally long period of time. In sense, the heat capacity of Earth causes it to act as a excellent thermal moderator. Ground temperature at 10 feet below grade is about the same as water temperature at depths of 20 to 60 feet. In the United States, average ground temperatures varies from 50 to 80 Fahrenheit depending upon the location. Because of these constant temperatures, soil above a 10 feet depth changes temperature much slower than does the rapidly changing air temperature. This slow changing characteristic is known as thermal lag. Thermal lag not only reduces the daily temperature swing below grade but also forces a lag in weekly and monthly average soil temperatures. For example, at a 10 feet depth, soil temperature lag average air temperature by about 3 months. Normally, there is a lag period of 1 to 1.5 weeks for each foot in depth below grade, down to about 10 feet where the temperature swings began to level off. So, ito yung table ng overall coefficient of heat transfer from insulated and insulated walls below. Yan. Yan yung mga heat transfer coefficient. Tingnan nyo na lang dyan. Tapos, ito pa yung the overall coefficient of heat transfer is based on the soil depth below grade. Yan naman yung base sa soil. Yan. Tapos, transmission heat loss in floor of on grade. For design purposes, the heat loss of a slab on a near grade is primarily from energy passing from the slab edge at the exterior building perimeter. Although the slab area away from exterior walls contributes somewhat to heat loss, it only accounts for a very small fraction, usually less than a few percent with perimeter insulation. Thus, transmission heat loss in floor upgrade is based upon length of exposed perimeter edge rather than the area of the slab itself. Heat loss through the exterior edges of a concrete slab on a grade or slab within 3 feet or 1 meter of grade is based on. So, ito ulit yung formula. Where rate of the heat loss per unit, UF is expressed in BTU over R minus feet or W over M. L is a lineal feet or meters of the edge of the slab exposes to the outside condition. T is the time period in hours, and Q is the quantity of heat loss in BTU or rate of heat loss. Value of UF are listed in Table 4.2. In colder climates, it is common practice to place insulation around the exteriors of the perimeter of the building. So, Table 4.2, rate of heat loss per unit length through the exterior edges of concrete slab on the grade based on the winter outside design temperature. So, ayun ulit yung mga katulad nung kanina. So, next tayo. Example 4.3, a house is built on a slab of grade foundation that is 25 feet 4 inches by 41 feet minus 4 in rectangular shape. Assume the outside design temperature is -5 Fahrenheit. Determine the rate of heat loss through the exterior edges of a concrete slab if the slab edges perimeter is insulated with 2 in the perimeter insulation, an R value or about 5. The house has 33.33 feet of exterior edges of a concrete slab. 2 or 25.33 feet minus 41.33 feet is equals to 133.33 feet. Yung Q is equals to U multiplied by L 40 BTU per hour per feet of edges. So 133.33 feet is equals to 533 BTU per hour. Determine the rate of heat loss through the exterior edges of a concrete slab if the slab edges is not insulated. The house has 113.33 feet of exterior edges of a concrete slab. 2 multiplied by 25.33 feet minus 41.31 feet is equals to 133.33 feet. Q is U multiplied by L60 BTU per hour per feet of edges. So, 133.33. So equals is 8,000 BTU per hour. So, doon nagtatapos yung aking part. Thank you.
Infiltration heat loss computation. Infiltration is the exchange of conditioned air with outside air. For example, pag taglamig, yung air na nasa loob ng building is lalabas siya at mapapalitan yon ng mas malamig na hangin na siyang mag-infiltrate sa loob ng building. So, yung infiltration air kasi is pumapasok siya through the opening of walls, cracks sa paligid ng bintana at pinto, and then sa mga butas ng electric outlet. The quantity of heat loss through infiltration depends on many factors, including inside-outside air temperature difference, wind velocity, occupancy pattern, furnace operation, and the physical condition of the structure. Wind is one of the factor kasi yung wind nagre-create ng pressure within the building dahil dito nag-i-increase yung infiltration rate. So habang lumalakas yung hangin, the amount of air leakage will increase. But if may mga puno or other pensa, isang lugar, maaaring maapektuhan nito yung amount of infiltration caused by wind kasi hindi na siya open space. Hindi na agad or may humaharang sa pagpasok ng wind sa isang building. The heat capacity is expressed in unit of British thermal unit per cubic foot, degree Fahrenheit, or watt per cubic meter, degree Celsius. The capacity of air will generally range from 0.014 to 0.018 BTU per cubic foot, degree Fahrenheit, and 0.26 to 0.35 watt per cubic meter, degree Celsius. So the lower value applies to higher altitude. Example, Denver. So it is common practice to use 0.018 British thermal unit per cubic foot, degrees Fahrenheit, and 0.35 watt per cubic meter, degree Celsius as the heat capacity of air in heating load calculation. Infiltration heat loss. Infiltration heat loss is usually a significant fraction of the total energy consumed in space heating or cooling a building. So there are two methods in calculating heat loss from infiltration: the crack estimation method and air change method. So yung crack estimation method is nagbe-base sila sa mga crack around the windows and doors, while yung air change method is based on the volume of structure or room. Yung etong air change method is usually ginagamit siya sa mga modern buildings. Air change for R is expressed in terms of the exchange rate of the equivalent of one volume of the space or room under consideration. 1 ACH relates to an infiltration rate equivalent to the volume of the space or room in 1 R. So, pag 2 ACH naman, it means twice na yung volume of the space na na-replace by infiltration. Instantaneous infiltration rate as low as 0.1 ACH and as high as 5 ACH. Infiltration rate of 1 to 2 ACH is usually na-encounter siya sa mga older building, while 0.5 to 1 ACH is sa mga new residents and buildings naman. One method of estimating infiltration rate. For tight, energy-efficient construction, the ACH is between 0.41 and 0.59. For medium construction, the ACH is between 0.69 and 1.05. For loose construction, the ACH is between 1.11 and 1.47. The air exchange rate are based on the outside design temperature ranging from -40 to 50 degree Fahrenheit and -40 to 10 degrees Celsius. The higher ACH value in each construction category is for the highest outside design temperature, 50 degree Fahrenheit and 10 degrees Celsius. So here is the formula of infiltration heating load and rate of infiltration loss. Infiltration heating load is equal to C times ACH times B times delta T times T. And rate of infiltration loss is equal to C times ACH times B times delta T. C is the heat capacity of air, ACH is the number of air change per hour, B is the volume of the space in cubic foot and cubic meter. Delta T is the inside-outside temperature difference. Example, calculate the rate of infiltration heat loss of a room with a 200 square feet floor area and 8 feet high ceiling. Use an inside temperature of 68 degree Fahrenheit, an outside ambient temperature of 0 degree Fahrenheit, and an hourly ACH of 0.5. Assume the heat capacity of air is 0.018 British thermal unit per cubic foot, So, using the rate of infiltration loss formula, substitute all the given number. So, para makuha mo yung final answer.
Ang topic ko po ay about sa heat loss from ventilation. Ventilation air is unconditioned outdoor air that is mechanically introduced into the building interior that, as a result, contributes to the building heating load. So when I say ventilation kasi, ito yung kailangan sa isang building para mag-remove ng stale air. Yung stale air na tinatawag natin, ito yung mga contaminated indoor air kung saan nagkokosto ng moisture, odors, gases. Pero kapag na-remove na to and mapapalitan siya ng fresh air, dun na mare-reduce yung accumulation ng mga moisture, odors, and other gases. Sa ventilation din kasi, ito yung nagke-create ng air movement para mag-improve yung comfort of the occupants. Then, ito rin yung ginagamit para makontrol yung exposure dun sa airborne contaminants. So, for residences, yung ventilation heat loss daw ay ini-ignore lang sa heating load computation. Kasi nga, it is not a code requirement and it is generally small. While the non-residential buildings daw, yung ventilation heat loss daw ay may significant consideration sa heating load computation. Kasi yung ventilation air is required sa mga buildings for occupant comfort and health. So, in large buildings naman, yung ventilation heat loss daw ay tinatrato or treated as a separate component of heat load. For example, ASHRAE standard 62 specified rates at which outside air must be supplied to a room, which is generally within the range of 15 to 60 cubic foot per meter per person, depending on the activities that normally occur in that room. So, i-assume natin na yung classroom daw ay may space na nakadesign for an occupancy of 30%. Then, the ASHRAE standard calls for a minimum outside airflow rate for the classroom of 15 cubic foot per minute per person. So, therefore, yung classroom daw, kailangan niya ng 15 cubic feet per minute per person to 30% or 450 cubic feet per minute. Sensible heat loss from ventilation air is based on the quantity and condition of the outdoor air. So, the sensible heating load daw from ventilation ay makukompute sa ganito. So, based on the outside design temperature and inside design temperature difference delta T in degree Fahrenheit and the volumetric airflow rate in cubic feet per minute, the constant 1.1 is based on the heat capacity of air under standard condition multiplied by 60 minutes in an hour, 0.018 British thermal unit degree Fahrenheit, 60 minutes per hour, 1.08 is rounded to 1.01. So, ito yung formula ng ventilation. Ventilation is equal to 1.1 multiplied by airflow multiplied by delta T. In metric SI unit, the sensible heating load from ventilation can be computed as follows. Based on the outside design temperature and inside design temperature difference, delta T, in degree Fahrenheit and the volumetric airflow rate, ito yung niya naman, formula. Ventilation is equal to 1.2 multiply by airflow multiply by delta T. So, halimbawa, example, a college classroom is designed for an occupancy of 30%. So, yung may isang classroom daw na design na ang kasyang katao o person ay 30. So, the ASHRAE standards calls for a minimum outside airflow rate for the classroom of 15 cubic foot per minute per person. The target inside design temperature is 72 degrees Fahrenheit and the outside design temperature is 3 degrees Fahrenheit. So determine the sensible heating load from ventilation. The classroom ventilation rate is found by ito nga 15 cubic foot per minute per person. Multiply by 30 person is equal to 450 cubic foot per minute. So, ito yung airflow niya. So, gamitin natin yung formula kanina. Yung ventilation is equal to 1.1 multiply by airflow multiply by delta T. So, magiging ganito. 1.1 multiply by airflow. Ano ba airflow niya? Ayun, yung 450 cubic foot per minute per person multiply by the delta T, yung temperature niya. Yung 72 degree Fahrenheit, yun yung inside temperature minus the outside temperature is 3 degree Fahrenheit. So, it is equal siya sa 34,155 British thermal unit per hour. So, yun lang po.
So this is our report, chapter 4.5. This is reported by Brisa Lipatsyag, which is me, and Ella Cartagena. So for first example 4.5, a college classroom is designed for an occupancy of 30 persons. The ASHRAE standard calls for a minimum outside airflow rate for classrooms of 50 CFM per person. So, yung college classroom daw is designed para sa 30 students. So, ano nga ba muna ang ASHRAE? ASHRAE is an American Society of Heating, Refrigerating, and Air Conditioning Engineers. So, the target inside design temperature is 72 degrees Fahrenheit and the outside design temperature is 3 degrees Fahrenheit. So, ang hahanapin natin is the sensible heating load from ventilation. So, para makuha natin yung ventilation rate, kailangan natin pag-timesin yung CFM per person times the total person, which is 450 CFM. Para naman makuha natin yung Q ventilation, kailangan nating pag-timesin yung airflow, which is 1.1, the delta and the CFM na total na nakuha natin kanina, which is 450. Tapos, ta-times din natin doon yung total heat sa lugar, which is the outside design temperature minus inside design temperature. So, ang total nun is 34,155 BTU per hour. So, as shown in the example 4.5, the ventilation component of the heating load building with high occupancy can be significant. Heating load analysis. The primary requirement for thermal comfort of a building occupants during cold weather is a comfortable inside air dry bulb temperature. So, para makuha natin yung temperature na maganda or comfortable sa isang lugar or isang room, kailangan natin makuha yung air dry bulb temperature. So, what is air dry bulb temperature? Ito yung temperature kung saan mas mainit siya kumpara sa wet bulb. Pag kasi wet bulb, may kasama na yun na wick and water. Heat introduced by heating equipments is constantly lost through the building envelope. So, syempre, kapag yung init na na-produce ng isang machine is hindi na sustain, syempre, mawawala din yun sa isang building. Calculation of the heating load consists of estimating the maximum probable heat loss of each room or space to be heated while maintaining a selected inside temperature during design outside weather conditions. So, para makuha natin yung heating load, kailangan natin ma-maintain yung nasa loob nun. Kung saan para makuha yon, kailangan natin computin yung nawawalang heat, tapos yung idadagdag na heat. Especially kung gaano nga ba kalamig sa labas. Ganon. Heating load computation methods. Heating load computation are made to size an HVAC heating system example is furnace, boiler, and its components, which are coils, ductwork, and piping based on heat loss and building performance at near extreme conditions. So what are HVAC? HVAC is heating, ventilation, and air conditioning system. There are several methods used to compute the heating load of buildings from a use of rule of thumb method. Example is 25,000 to 75,000 BTU per hour, 1,000 feet squared of floor area based on geographical location to detailed sophisticated computer modeling. So, sa pag-compute ng heating load ng isang building, gumagamit tayo ng rule of thumb method. So, ano nga ba yung rule of thumb method? Rule of thumb method refers to the principle that is not applied to be extremely accurate but extremely reliable. So, ginagamit lang to kapag wala tayong dalang mga equipments para ma-measure yung init sa isang lugar. And to detailed sophisticated computer modeling. So, yun nga yung mga ginagamit nating methods to compute the heating load of a building. So, for heating load to be accurately computed, the areas of the building envelope where the heat transfer occurs and heat transfer properties of many different construction assemblies, example is walls, windows, doors, and ceiling must be identified. So, pag magko-compute tayo ng heating load ng isang lugar, especially pag mga large buildings, kailangan nating isama sa i-compute or i-compute ay yung mga walls, windows, doors para malaman natin kung gaano ba magiging kainit sa loob ng lugar na yon or sa mga kwarto doon. Heating load is computed on a basis of these characteristics. Except in very small buildings with a single zone, load calculation should be made on a room by room or zone by zone basis because an HVAC system must be properly delivered to heat to specific rooms or spaces. So, kapag naman maliit yung lugar, kailangan lang natin siyang i-compute room by room or zone by zone para malaman natin kung properly delivered or properly ba na nade-distribute yung init sa isang lugar or sa isang space. Heating load computation methods. Procedures that use and precise heating load calculation results should be used to compute the heating load of a building sizing. Unsophisticated rule of thumb method should only be used as approximate for preliminary design and should never be used to accurate actual system sizing. So, ayun nga, yung rule of thumb method, hindi yun dapat gamitin sa actual system sizing kasi hindi nga siya ganon ka-reliable. REE publishes procedures for accurately computing that design, heating, and cooling loads of the ASHA Handbook Fundamentals, the Air Conditioning Construction of America Incorporated, which is ACCA, and the Air Conditioning of Refrigeration Institute, which is RII, jointly developed Manual J residential load calculation, another widely accepted method of calculating the heating and cooling loads under design condition for residential structures. So, etong mga institutes na to, gumawa sila ng bagong procedure para mas makompute natin yung heating load sa isang lugar. ACCS manual and commercial load calculations can be used to estimate heating and cooling loads for small and mid-sized commercial structures. So, yung mga binigay nilang procedure, magagamit lang natin yon sa maliliit or sa mid-sized na lugar. Hindi yun pwede sa mga big buildings or yun nga, yung malalaking bahay, for example. Design conditions. Designer use winter design conditions as basis for computing the peak operating conditions which HVAC system and equipment must operate during heating season. So, yung mga designer, gumamit sila ng winter design condition para malaman nila kung hanggang gaano ba kainit or gaano ba kalamig yung aabutin sa isang lugar on a certain place and on a certain period of time. Inside dry bulb temperature and outside dry bulb temperature are used as the basis for the design condition. So, ayun nga, yun mga ginamit na lang basis for design conditions. So, inside design condition. Inside design conditions are the target and their environmental conditions intended to achieve thermal comfort. So, ito yung mga design na ginagawa ng mga engineers or electrical engineers para magkaroon ng init sa isang lugar. As introduced in Chapter 1, thermal comfort is associated with many variables including air temperature, radiant temperature, air movement, gender, clothing, activity level, age, and adaptation to local climate. There is no single set of inside design temperature/humidity levels recommended to achieve acceptable comfort. So, the typical inside design temperature range from the heating season in most U.S. homes are usually the range of 68 to 72 degrees Fahrenheit, 20 to 22 degrees Celsius. So, ito yung mga temperature range na karaniwan na experience sa US kasi di ba nga malamig doon. And commercial buildings in temperature and humidity levels should be in accordance with the comfort criteria establishing ASHRAE Standards 55 to 2004.
Good evening, I am Elame M. Cartagena, and this is the continuation of Inside Design Condition reported by Brisadly. As you can see, this is the table of suggested indoor design, dry bulb temperature, and related humidity ranges from selected companies. Lower temperature typically apply to the heating season. Code requires may vary by jurisdiction. For example, one code requires that indoor design temperature shall be 70° Fahrenheit for heating and 78° Fahrenheit for cooling. Yung table na to, send na lang namin to sa inyo. And let's proceed sa outside design condition. Outside dry bulb temperature based on climatic condition at the specific geographic location are used as the basis for outside design condition. Yung outside dry bulb temperature, katulad ng pinakita ni Brisa kanina, it refers basically to the ambient air temperature. Climate condition used are from long-term historical database and do not represent an actual year, but are statistically representation of average long-term condition. The heating load is estimated for winter design temperature occurring during early in the morning hours. Yung heating load naman for winter ay nangyayari yan sa mga madaling araw na oras. It is not economically to use the minimum record outdoor air temperature as the basis for the design because it leads to equipment oversizing to meet demands that seldom occurs. Instead, design values near the extreme condition are used. Ito naman, hindi nila sinasuggest na gamitin yung minimum record bilang batayan para sa design. Kasi daw, it can lead sa sobrang paggamit sa kagamitan upang matugunan yung mga demands. Sa halip, ang mga halaga ng design, in extreme condition, yun yung ginagamit nila. In Denver, Colorado, the 99.6 dry bulb temperature per heating is negative 3° Fahrenheit. The 99.0% dry bulb temperature per heating in 3° Fahrenheit. The 99.6% condition represent the most extreme design condition and the 99.0% the least extreme. The designer must choose with a set of design temperature condition applies a particular project. Traditionally, the 99.6% design values are used for computation involving light mass residential building. And for example, yung house, apartment, townhouse, manufactured home, dwelling, condominium, convent, monastery, hotel, and so forth. For massive massage structures that have a little glass, the 99.0% the sun value should be used. Design temperature difference or delta T. In heating load computation, the design temperature difference or delta T best found by subtracting outside temperature from inside temperature. For example, in Denver, yung inside temperature is 72° Fahrenheit, ima-minus mo yun sa 99.6% na outside design of negative 3° Fahrenheit. Tapos, yung makukuha mong design temperature difference is 75° Fahrenheit. The 75° Fahrenheit is substitute for delta T and heat transfer equation to find the heating load at the design condition. Temperature and unheated spaces. To determine the heating load from the heat, add space to the unheated space. For example, from the house to an unheated garage. It is first necessarily to determine the temperature in an unheated space. The temperature in an unheated space will lie somewhere in the range between the inside and outside temperature. Yun, katulad nga sinasabi dyan, mas kailangan muna nating alamin yung temperatura ng unheated space. And yung unheated space, nagre-range siya sa inside and outside temperatures. Temperatures in unventilated spaces. The temperature in unventilated spaces will vary depending on transmission characteristic and quantity of surface area adjacent to the two heated rooms compared to transmission characteristic and quantity of surface area adjacent to the exterior. Yung temperature sa mga ventilated spaces ay syempre magkakaiba yan depende sa katangian tsaka sa quantity ng isang lugar. Tapos, sabi dito, in theory, this temperature can be estimated using the following equation. So, ito yon. Ito yung formula niya where T sub U is equal to temperature in unheated space, degree Fahrenheit or Celsius. Yung T sub I naman, inside design temperature of heated room. Yung T sub O, outside design temperature. A sub 1, A sub 2, A sub 3, yun yung area of the construction assemblies that are exposed to the heated space. Tapos yung A sub A sub B, A sub C, sila yung area of the construction assemblies that are exposed to the exterior. And yung U sub 1, U sub 2, U sub 3, sila naman yung coefficient of heated transmission for the construction assemblies in A sub 1, A sub 2, and A sub 3. U sub A, U sub B, and U sub C, it is the coefficient of heat transmission for the construction assemblies in A sub 2, A sub B, and A sub C. Tapos ito yung niya, yung formula niya na sinasabi ko kanina, yung T sub U is equal to T sub I, open parenthesis, A sub 1, U sub 2, plus A sub 2, U sub 2, and so on and so forth.
So, ako po yung next reporter. I'm Angelica M. Manlapig. Yung topic po na na-assign sa akin is all about temperatures in unheated attics, basements, and crawl spaces. Sabi po dito, to accurately calculate the heating load, kailangan natin estimate yung temperature ng unheated attics, basements, and crawl spaces adjacent to the conditioned spaces. Kasi po yung mga temperature ay hindi basta-basta nakakalculate, lalo na kung kino-consider natin yung mga natural ventilation saka yung temperature ng earth. So, the designer can use the following as guidelines for estimating the air temperatures in unheated spaces. So, sabi po dito, yung designer po ay gumagamit rin ng mga guidelines para ma-estimate yung temperature sa mga unheated spaces. So, yung mga unheated basements and crawl spaces po ay matatagpuan below the ground, kadalasan sa mga building between first and ground floor. So, when we say unheated basements and crawl spaces, sapat na espasyo lang para makagapang yung tao. Normally, the temperature is coming from the midway between the inside and outside design temperature. So, kapag ang basement at crawl spaces ay may open windows or space na nag-aalaw sa hangin makapasok, ibig sabihin ay mas mababa yung magiging temperature niya kaysa walang windows or vents na paglalabasan ng hangin. Para sa crawl spaces or attic spaces, sinaseparate siya ng dalawang high levels of insulations. An indoor air temperature very near outside air temperature ay talagang pwedeng gamitin. Usually, nasa range siya ng 2 degrees hanggang 10 degrees Fahrenheit, 1 to 5 degrees Celsius about outside air temperature. And if an operating heat unit kagaya ng boiler or turbines and uninsulated piping or ductwork is located in the basement, crawl spaces or attic spaces, Yung indoor temperature niya ay magiging higher kaysa kapag ang heater ay located kung saan lang. Sa maikling paliwanag, so the designer must use judgment in approximating the temperature to use in the heating load calculations for unheated attics, basements, and crawl spaces adjacent to conditioned spaces. So the next topic, internal heat gain. Building heat gain is sensible and latent heat emitted within an indoor space by the occupants, lighting, electric motors, and electronic equipment, and solar heat gains from windows. So, ayun na nga, nasabi, nagkakaroon ng or nabibuild ang heat gain within the indoor space by the occupants. Tapos, gaya na rin ng sa lighting, electric motors, and sa electronic equipments. Lahat ng yun pwedeng mag-cause ng pagbibuild ng heat gain. Halimbawa, an occupant gives off about 250 British thermal unit per hour. The heat given off by a 75 watts lamp, a kitchen range may generate heat of 7,000 British thermal unit per hour, about 2,000 watts or more when a cooking family meal. Depende sa ginagamit or kilos ng gumagamit kung ilang heat yung gigain, at lahat ng yun pwedeng maging reason para makalikha or mag-generate ng heat. So, this and other sources account for a considerable heat gain. So, ito yung ibang sources account ay para sa considerable heat gain. Ito ay isa sa rason kung bakit ang isang interior ng building ay na-maintain yung komportableng temperature kahit na yung outside temperature ay bumagsak. And additionally, yung mga buildings, lalo na yung mga heavy thermal mass, ay may ability at coast past the coldest part of the day. So, yung resulta ng heat gains at epekto ng thermal mass ay yung residential structures ay kailangan or require yung space heating, at pwede lang ito kapag ang outside temperature ay bumaba sa 15 degrees Fahrenheit or 9 degrees Celsius na mas mababa sa temperature ng isang lugar o nasabing lugar. So, well-insulated building or buildings with heavy thermal mass. So, ito yung lugar kung saan kailangan ng onting dagdag na heating or cooling sa lugar na ito. At dito rin sa insulated buildings ay may isa lang na kailangan, at ito nga yung space heating na mas mababa kumpara sa outside temperature. Yung mga lugar na may malaking space gaya ng simbahan, paaralan, sinehan, or iba pang mga maluluwang na buildings, those are having significant internal heat gains na manggagaling sa mga ilaw na nandoon or mga electronic tools na nagkakos ng heat, and it may not have space heating load until outside air temperature drops substantially. So yung mga buildings na ito kailangan ng heating system kapag low of occupants or hindi kadalasan nagagamit, halimbawa kapag bakasyon at hindi masyadong gamitin ng lugar gaya ng school. Pero ibang buildings ay pwede silang mag-rely upon heat rejected galing sa mga equipment tulad ng refrigeration at grocery store. So generally, heating load computations are made with the assumption that internal heat gains do not exist. Any heat gains during severe winter conditions serve as a factor of safety in design. So, proceed tayo sa general procedure. So, yung process ng estimating design heating load involves siya sa computations of heating losses in each of the individual spaces at design conditions. Heating load calculations are carried out for each space or zone within the structure. At yung process kailangan room by room basis para sa sizing of equipment gaya ng ducts or foil unit kung saan mag-serve to para mapadali yung individual spaces. So, una, determine natin yung outside temperature. So, pangalawa, Select natin yung inside temperature para ma-maintain yung heated spaces during design conditions. So, pangatlo, estimate air temperatures in adjacent unheated spaces. So, pang-apat, i-determine yung overall coefficient of heat transfer para sa construction assemblies na nakapagitan sa heated spaces and outside air. So, pang-lima, i-calculate yung net area ng lahat ng construction assemblies na mapaligid sa heated spaces and dun sa outside. Then use inside dimensions. So, 6. After nun, compute heat transmission losses for appropriate construction assemblies by using methods previously described. So, 7. Compute losses associated with infiltration. So, 8. If mechanical ventilation is used to maintain inside air quality, determine the rate of air exchange and calculate ventilation loads based upon design condition. So, sa pangwalo po, yung kapag ang mechanical ventilation daw ay nagamit sa inside air quality, determine natin yung rate ng air exchange tapos i-calculate ulit natin yung ventilation loads based upon design conditions. So, lastly, some transmission and infiltration losses and ventilation losses. So, ito yung nagpapakita na or nagre-represent ng design heating load ng space at design condition. So, yun lang po.
Monthly and seasonal calculation. In using the degree day concept, the equation for transmission heat loss over an extended period may be simplified because degree days are the product of temperature difference or delta T and time in days instead of hours. It is possible to substitute degree days for delta T and T, provide days are converted to hours. So we will have Q is equals to U multiplied to A multiplied to 24 and multiplied to HDT, where U is the overall coefficient of heat transfer in BTU per hour, degree Fahrenheit, square foot. A is the area of the assembly in square foot. 24 is an hour per day conversion. HDD is degree days in degree Fahrenheit. And Q is the quantity seasonal heat loss through the construction assembly in BTU. Similarly, the equation for air infiltration may be substituted with 24-hour a day and degree days to estimate the seasonal heat loss from infiltration. So here's the example. Example number 1. A house in Denver, Colorado has insulated walls. U is equals to 0.073 BTUR degree Fahrenheit square foot. Assume the house has 886 square foot of net wall area. Calculate the annual heat loss through the insulated walls over a typical heating season. So, from the table conversion, annual heating degree days in Denver, Colorado are 6,128 degree Fahrenheit. So, applying the formula, Q is equals to U times A times 24 times HDD. So, we have here Q walls is equals to 0.073 BTU per hour, then times 886 square foot times 24-hour a day times 6,128 degree Fahrenheit. So we will be having 9.5 MMBTU per year. So approximating heating fuel cost. The following method can be used to approximate the fuel consumed over the heating season based on the total
design load. Heating degree day seasonal efficiency of the heating system or appliance. The design temperature difference or delta T design and the heating value or heat of combustion value of the fuel. So we're gonna have here fuel consumed is equals to DL sub T or the total design load, and then multiply it to HDD and then multiply to 24 all over N sub HS or the heating system or appliance multiplied to design temperature difference or delta T design times the HV or the combustion value of the fuel. So seasonal efficiency varies with type of heating system or appliance. The seasonal efficiency of various types of heating systems and appliances are provided in table 4.4. Approximate heating values of common heating fuels are listed in table 4.5. These values are general references for residential heating applications only. Commercial and industrial users should obtain more precise values from their fuel vendors. So, here's the example. The home in example 4.7 has a heat loss of 46,750 BTU per hour. Assuming a design temperature difference of 73 degree Fahrenheit, a climate with 6,000 degree Fahrenheit times per day, and a natural gas-fired medium efficiency and induced draft furnace at a sea level. So letter A, determine the fuel consumed over the heating season. Fuel consumed is equals to DLT times HDD times 24 all over N sub HS delta T design times HV. So we're gonna be having here an answer of 1,119 CCF. And then letter B, at $0.90 per CCF, approximate the fuel cost over the heating season. So fuel cost here is now equal to 1,119 CCF multiplied by $0.90 per CCF. So we will have here the fuel cost of $1,007. Limitations. This method of energy estimating is rudimentary and provides only rough approximations because it is based on the degree day method and does not account fully for system efficiencies. Studies indicate that building costs through a portion of the heating season, resulting in a load that is less than that computed in a moderate climate. The seasonal load will be 20 to 30% less than the computed load using the degree day method of energy estimating. On the other hand, additional system losses have the effect of increasing the load because some of the energy consumed is waste heat. These efficiency losses can be significant, particularly when the additional part load efficiency losses are considered. These factors are opposite in effect and have the outcome of roughly canceling one another, which results in an estimate that more closely represents actual performance.